So the next, so one of the questions that was asked in the previous section, in the previous session was, okay, how do we get the models, right? How do we build the models? I'm a circuit guy, and then there is this system level guy, he's operating. He wants my model to be, he wants my circuit to be given as a behavioral model. Okay. Still people are settling down. So how do you bring a behavioral model from your circuit into your system simulation, right? So that has been traditionally a big pain, where as we go everywhere, that traditionally what they said is, oh, we don't know who my system engineer is, that's in a different building. I just build my circuits, and the system guy says, I don't know how to extract a model from them, because for every designer, we need 2 verification engineers. We don't have that luxury. We have not seen many companies come and say, we have 2 design engineers and 1 verification engineer. So there is nobody there to extract the models accurately and then give it to the system level guy. So because of that, the system guy says, okay, whatever is available to me, I'll take it, and then I'll just do rough calculations, and then I'll just live with it, right? That's not the where we want to leave it. We want to help the industry actually to integrate. So instead of the circuit guy going and then trying to learn the system tool, why not bring the system tool into the circuit environment, so that as they design, they can say, okay, let me substitute my circuit into the block diagram that system person may give it, and then see what the performance is. For example, going back to the amplifier design, what if the amplifier designer at that time had this template where he can put it and then say, here is my circuit, I'm putting it here, and then I want to see the performance. So that is what we call Explorer, the system explorer for the circuit designers. All right, so that's the 4542E, the part number, and we'll go a little bit details into that. There's a lot of text. Don't focus on the text. Just get the concept. So how many of you use ADS? Just 4 of them? Should we be worrying? Okay. So do you use any other circuit design tool? Of course. Which one? Virtuoso or Cadence or anything else? Yeah. ADS. Of course, ADS is easier. If you were to be living in, let's say, you're an IC designer, and then you have to do that, there are easy ways to bring the circuit design from Virtuoso into ADS. If you know it, that's fine. If you don't know, we can easily bring it. And then once the circuit lives in ADS, you have the access to the system tool. You can put your circuit into the system. That's what we are going to show here. Okay, what are we dealing with here is the RF simulation, RF impairments, of course the analysis, and then the RF models. Those are the things, I don't know which phone is this, but in all phones that is the same thing that happens. So we have the circuit derived nonlinear models. That is the most important thing that we need to have. Oops, I don't know, I can't progress. What is happening? All right. So the new technology is, some new terminology that has come in, extracted behavioral model. So let us say you have an amplifier. How do I model an amplifier? The simplest model ever. Can you think of it? Just multiply with a number. That is an amplifier, right? You can start like that, but that is not how the amplifier behaves, right? And it does a lot of other things not just by giving the gain. It likes how much power goes in, what is the bandwidth of the signal. There are a lot of things going. So we need to model the amplifier with a little bit more parameters. So if you go to the vendor catalog, they will give you gain, noise figure, 1 dB compression point, saturation, third order intercept point, second order intercept point, And some companies go even further. They say, okay, I'm going to give you AM to AM, AM to PM, and then even those are not enough. They are only parametric based amplifier model. They will bring you pretty good accuracy. If it is a linear amplifier, if you're operating in linear range, S parameters will give you almost a close to perfect answer. But if you're doing a little bit more into the non-linearity, then of course you get into this requirement of my signal is broadband, so I need to have the frequency response, I need to know the phase response of the amplifier, all those things that we need to know. But even that may not be sufficient. There is nothing like substituting your circuit there, right? So, but again, you have to extract. There is no way all that happens at the device level physics can be turned into a behavioral model. But you can decently turn a lot of things into the behavioral model, and that is what we mean by extracted behavioral model. And the symbols will change the moment you designate your circuit to be a extracted behavioral model. It will appear like that. So again, I'm just going to focus on the concept of it and then see if we can move very quickly. So let us say you have an amplifier, right? Oh, there is a little, my name is RF System Explorer. Okay, that's a little story by our factory. So again, because there are only 4 ADS users, I don't have to be really concerned with it. But if you are, even for those 4 of you, you might say that there was already a budget analysis tool in ADS. Why do I need another system tool to be brought in here for me to do that? If you have not recognized, that is obsoleted last year. So there is no more lineup analysis in ADS. You have to do in the hard way, of course. Every circuit, if you simulate and put them together, it will, overall, you can run harmonic balance, or you can run envelope analysis or time domain analysis. You can get the performance. But again, we already went through that. It takes a long time to do at the circuit level. So that is disappeared. That's the reason this system level tool is now brought into the ADS simulation. These are details. We'll not go into this. Let us just go and then visit very quickly. What happened? Yeah. So the goal for this bringing the RF System Explorer is for the circuit designer not having to learn all that I have shown, right? To the extent it's a simplified, more focused for the circuit level guy to be able to put their circuits into the system level simulation. So when they open up, they come up with some kind of a UI, and then it is not the complete system view tool that is brought into ADS, but a portion of that is appropriate for the circuit designer that is brought into ADS. So let us say you have put 2 amplifiers together, and then you are looking at the spectrum, and then you're looking at the level diagrams and things like the cascaded gain, etc. And you want to then substitute your circuit. So what happens is in the UI, instead of behavioral, sorry, this is a small text, here it says behavioral, you can designate to be extracted. So what actually happens is, I don't have the slide, you actually open your circuit simulator, you open the schematic, and you have in the schematic, actually you have the System Explorer. So if you create that will open a new view, new cell. It's a new cell that gets created. Typically it gets created with the name RF SE1, that is the default, RF System Explorer. Under that, it will, initially we are providing some templates for you can open the template. So the template can be a simple amplifier, but you can add parts. The parts are here. You can add to whatever the default that comes, and then you can put them together. After you put together the chain in ADS, you're all still sitting in ADS, but this looks more like the other tool, the system view. And then you can, at that point, go into this UI opens, you can select the part and say extracted. After that, you're going to tell which schematic, your circuit schematic, which one you want to extract the behavior model from. So you're going to specify the schematic. That's what probably here, well, both of them are selected as extracted, and the schematic is wideband amplifier 2-stage and wideband amplifier 1-stage. So there are two schematics that we designated them as the candidates for extraction. Then it goes into the final tab here, again, small text, excuse me for that. So characterize, if you hit this button, you don't have to do anything. It goes, it runs the necessary harmonic balance simulations, and it's like it creates a test bench behind the scenes. It's all automated. And then it will capture the behavior of the amplifier in the form of what we call MDIF format. Again, some of this terminology may be new to you, but it's a multidimensional interchangeable format. It's a text file that will describe the performance of the amplifier, and the amplifier performance is described as, let's say, what are all the things that we need? We need the gain, the noise figure, the 1 dB compression point, the saturation, third order intercept point, maybe input-output mismatches, so the Z in, Z out you can get, and then the reverse isolation. So you capture all these as a function of frequency, and these are all captured as a function of power, right? Of course, it does the power sweeps and derives these parameters. If you have any other dimension in future, that will also be added. Yes?
You just said something. So the S parameter set that this parameter is built on changes after drive level, so there's multiple copies of gain. Is there gain compression represented by another table of S parameters?
No, it runs the power sweeps, and then from the compression curve, it derives the IP3.
Oh,
yeah, it does automatically all those things. We don't have to do anything. It just does everything. It's almost like putting a network device to a network analyzer and pushing the button. That's what you're trying to do here, excepting that you're doing an ADS.
Is this RF System Explorer part of ADS, or it's part of?
It will be part of ADS.
Will be part of ADS.
I mean, it is part of ADS. Let me put that way. But it's an external tool. It's not inside ADS, but we have ways of putting the menu picks in ADS, but what opens is outside of ADS. So it doesn't look like ADS schematic. It is a other tool. That schematic comes in here, but very easy to understand.
Is it part of ADS core, or is it additional license?
Oh yeah, there is an additional license. There is an additional part. There is an additional license. Yeah, it carries different things because it's in the. This is right now what we are showing is the phase 1. It is in a decent shape, but a lot of development will be going on in future into this.
And once you have the model, you take it to Spectrasys, and then you can run yours.
Oh yeah, once you are done with it, you are going to characterize, and then you hit, let me go back to the UI, and you're going to, oops, where is that? Okay. I don't have a good way to show it. It's a very tiny green play button there. You see that on the menu?
Yeah, I see it.
That when you push that, it will do the RF lineup analysis, the one that I have shown previously. So it does the analysis. What you're doing is you're asking the tool to extract a good behavioral model for your circuit and put it into the system context, and then run the system analysis there for you to be able to see the outputs. So what kind of outputs that it generates? This is what happens. Your circuits, both the circuits are used to be extracted into behavioral model. This is the behavioral model. It's a text file, and it can be reused if you want to give it to somebody. This is my amplifier, another system engineer, and then he can take it and put it into system view outside of it. And then the performance is in terms of a table, a spectrum, a level diagram. We can also always extend the measurements, the kind of measurements that you want to do. And so between these two, I will just switch quickly. See, there is a slight performance change because of the behavioral models, right? And you will be able to construct the more elaborate models for your circuits at that point, and then run the system analysis. And there is also, once we provide a script there, and when you push that button, it will go and capture multi-page document of all the measurements, IP3s, and then the entire performance of the system. And you can actually modify the script, which is a Python script. You can modify what else you want to add. So you can designate all the measurements that you want to do. So it produces a PDF document at the end of the day, performance of the system with your circuits sitting into the system. Right? That's this tool is all about. So the next one is a case study. One of our colleagues who worked on vector signal generator in the past, and the evolution of the vector signal generators. You see them. That some of the
In the previous session, you showed how we can bring the circuit into the system design, system view.
Yeah.
Here you showed the other way around. So these two are pretty much the same, right? Two way of
Oh, yeah, yeah,
combining
yeah.
system with circuit.
Yeah.
But
what
the
we have
result
done
is
is
the same, right?
what we have done in the phase one is the RF lineup analysis, the Spectrasys portion of the system view, we brought into ADS. We have, I'm sure there are plans in future also to be able to bring the time domain analysis also here, so that you can put complex waveforms into your system with your circuits sitting in there and verifying the end-to-end analysis. That's the goal.
Does it support Verilog 8 model generation?
No.
Because you can take it back to ADS and run your simulations there.
Yeah.
The model
Yeah.
much faster. You
We
need a separate tool.
System View does support Verilog, but we haven't visited in a while. But that requirement has recently come up. I think we can run. The only thing is we have to use Model Sim or Questa Sim as the interpreter for us to be able to run the Verilog model. As long as if that is acceptable, we have a solution. Yeah.
Does Keysight have any equipment that can generate the same file, behavioral model from the measurement?
Fantastic question. We are talking to our hardware colleagues. There are already some personalities on the network analyzer to give you some MDIF files, but we have to make sure that will be our goal in future. Either you can generate from ADS, or you can generate the model from an instrument and be able to substitute into your other system. Yeah.
Yeah, because in most cases we don't have access to the component design buy from the vendors, and
Yes.
sometimes, most of the time, this data is not available, right?
Right.
So we'd like to buy the component
And extract the
it
model.
into
Yeah.
your design, right?
Absolutely, absolutely. So if you look at our tool, right now we have a number of parts, mini circuits parts are there, models are there. They measure every single day, they measure thousands of parts, and then they provided a library into the tool. And then we also have analog devices. Models are there in the tool, and then a marquee microwave. Recently, they showed a lot of interest to put their library in here. So we are getting interest from the vendors to put their libraries here. It is going on. But you are to be able to extract your own if you have the measurement set up. Yeah.
And this MDIF file, as you said, includes the small signal and large signal data. So you no longer need the X parameter, for example, measurement for amplifier with your network.
It's
Right? I mean, you can extract the small signal and large signal in one measurement and put it in your design and system design tool and do it.
Right. So I haven't gone into the details, but even if you take just the amplifier model, right? Before I go into the amplifier, all the passive linear networks on your system, they're all perfectly characterized with S parameters. So touchstone file is wonderful. It's gold, and then if you measure that, you are able to model your part very accurately. Of course, complexities come through. If you're talking about a phase shifter with 64 states, then you have 64 S parameter file for that, characterizing that part. And then if you're doing at 3 temperatures, then 3 multiplied by 64 will be the number of files. So how do you handle that? We handle the multidimensional S parameters as well. That's called S2P MDIF format. And then our network analyzer can actually output that. So we can absorb those kind of models. Coming to the amplifier, there are so many ways to model the amplifiers, depending on the context. So starting with linear amplifier, it can be as simple as capturing a S parameter data with noise parameters, of course. And then going a little bit more, all the data that I'm showing, the system parameters here, the extracted model, this one. So what I'm capturing here is gain, noise figure, 1 dB compression point, the line, whole thing. If you capture that as a function of frequency, and if you capture that as a function of temperature, or if you want to capture that as a function of bias, or something like that, it becomes, yeah, amplifier model. So
I mean, as a function of power, right? You feed the power as well, right? So
the power is embedded here. These are nonlinear parameters, right? The IP3, IP2, they are already derived from the sweeping the power. So the model knows what to do with the incoming power, how to produce the output. So that's not the problem. Now, making it multidimensional becomes more challenging, but it still doesn't answer one question, is it doesn't have if it is a power amplifier, if the load is changing, the amplifier should change its behavior, right? So that is what we call load pulled model. And then it is not part of RFSE yet, but it will be in future. But we do have solutions for that. One solution is X parameters. If you extract X parameters as a function of load, that becomes the best model for the amplifier to be sitting in here. So again, there are so many ways to cut this amplifier modeling, which can be whole day discussion. Last year, we also introduced what we call dynamic gain amplifier modeling. If you search the literature, DGA, it is already there. We may have Keysight application note as well. So that not only captures the nonlinearity, but it also captures the memory effects of the amplifier. So again, depends on the fidelity you increase on the modeling. We have answers, but not everything is there in RFSE, but we have solutions for all of those areas. So
my first question, this capability is not available yet, right? Extracting this
it is right now.
From the measurement.
Oh, from the measurement, not yet. Not yet. But it can be easily be done. We can discuss that. All right. I'll just breeze through this very quickly, if you don't mind. I have only 10 minutes left. So this is a chain that was put together, and then doing some analysis and showing the results. So I'm not going to go through this portion. I'll jump into the DPD, digital predistortion, next session very quickly. So please excuse me for that. Again, this is what we call simulation-based EBM. So we have terminology already reserved for your question. This is called EBM. EBM is extracted behavioral model, right? SEBM is simulation-based extracted behavioral model. We also have the path towards MEBM, measurement-based extracted model. So the terminology is invented already. The process is not. They have not, implementation is not done. So you can measure all those top level measurements. You see that they're all easily measurable within this environment, the RFSE environment. You see the pretty detailed block diagram that is evolved here. This is all in the ADS context. You will be able to do that. And then design your entire system with your circuits sitting in the system. That's the whole concept. If you walk away with that concept, we can work out all the details if you are interested in trying out beyond that point. So there is another explorer, again for circuit designers. So traditionally what happened is you designed a power amplifier, and then people put it into the system, and then they say that, oh no, the linearity is not enough. I have to back off 10 dB or 15 dB. So you designed a 100 watt amplifier, and they're going to use it like a 1 watt amplifier, let's say, or 10 watt amplifier. So there is so much inefficiency. You're wasting so much power. You designed for 100 watts, but you have to use like a 10 watt amplifier because of the requirements of the linearity. You don't want to distort your information, your signal. So the solution for that is traditionally, okay, and I know I can distort my waveform going into the amplifier so that it counters whatever the nonlinearity in the amplifier, and it produces improved linearity at the output. That is the concept. That has been there for 30 years. We all know that. And digital predistortion is you take the output waveform, you know the input waveform, and then you digitize, you somehow come up with algorithms, and then you modify the input waveform in such a fashion that the output comes cleaner. It's not going to be completely perfect linearization, but it will reduce the spectral regrowth at the output. That's what is called DPD. And traditionally, it has been being done by system guys, the DSP experts, what we call, and then they say, okay, give me a model for your amplifier. Again, the same barrier between the system to the circuit. And there is no easy way you can extract a model and then put it in there. Now, for DPD, you really need very high fidelity of your circuit to be able to, because you're operating on that. Much deeper fidelity is required than a simple behavioral model that I have shown. So we need to bring the whole process from the system level area into the circuit level area. That is what the digital predistortion explorer for the circuit designers is all about. So when as a circuit designer, I can go into ADS and then I can launch. I can say, okay, you are in your circuit schematic. You open your circuit schematic and then you have a menu pick. You say the DPD Explorer. Then it comes with this UI and it will guide you from there. So it will let you decide. If you click on each one of these blocks, it will open up a next UI, and then it will let you set up what kind of waveform you want to put through your amplifier, right? And then sometimes, this is something that system level people do, that they massage the waveform to reduce the peak to average. The lower the peak to average, the better for the amplifier and even better for the DPD algorithms to linearize the amplifier. And then you go into the, so here you reduce it, and then if you push the button, it does the analysis, and then it comes with some kind of a coefficients that you can use to compress, or that you can use to distort your input waveform, so that when it goes into the amplifier, it produces output which we can analyze in terms of modulation analysis. So you can look at the EVM, you can look at the ACPR and things like that. That's the whole process that goes on. And the best part is ADS works under Windows, ADS works under Linux, right? When you are in, it is platform agnostic, operating system agnostic. So the DPD as a initial implementation also implemented in Linux. So whether you are in ADS in Windows or Linux, you have the access to the same application. So here is what happens. PAE, power added efficiency, is the measurement that, it's one of the measurements that you can do it. And here is the block diagram that allow you to do it. These are the measurements. At the end of the day, when you do the analysis, it produces ADS data display. That is the beauty of this. You're already familiar with ADS data displays, right, as a circuit designer. So you can see that, you can probably plot more metrics if you need to, but it shows some of the important things at the top. You see the ACLR and then the EVM, and then one of the metrics to tell you that how good was your linearization is normalized mean square error. There is a metric that shows. So what it is doing is, it is capturing the output waveform. You know what the input waveform. So from these two pieces of information, it is able to extract what do I need to do for the input waveform so that it comes out cleaner. That is the whole process. So a lot of algorithmic work goes behind scenes. So if you invented an algorithm, you need to know how accurate it is, how well it is performing. So that is what we call NMSE. So Keysight provides a couple of algorithms. I mean, we have multiple choices inside, only to demonstrate. Again, I want to be very cautious with this. Only to demonstrate, not to actually take away this algorithm and then implement it and then come back to Keysight and say, okay, it's not working. Okay, so please be careful with that. The whole idea is to create your own IP, to provide you a platform where you invent your own algorithms that will work through the platform. What we are providing is a very accurate modeling of your circuit, the amplifier itself. That is the key thing that we are providing. So when it operates, so it has to produce an output waveform, right? So you have an input waveform, so there should be something going into the amplifier. So what kind of model we are using? There are multiple ways it does. So when the waveform goes, when you hit the simulate button here, it goes into the circuit, and then it performs a number of simulations behind scene. And then it can capture either X parameter file, or it can capture what we call dynamic gain amplifier model. Though both of them are very accurate, or it can even co-simulate, which is a little bit slower process, but it does a very high fidelity model. It extracts and then operates on that. So it creates a model, and then it computes the coefficients that are required to. Extending this into, so the amplifier, a lot of architectures are there, right? Class A, B, C, and then Doherty amplifiers are there. But one of the things that is new that has been introduced is envelope tracking amplifier. Familiar? Envelope tracking amplifier, which is very efficient by nature. So that is also included into this simulation. So here is what happens in the amplifier. So if you have a fixed supply, and then the efficiency is very high when you are producing high output power, right? But when you are not producing very high output power, when the swing is low, but you're still consuming, that yellow portion is what shows the energy wasted. It is still, you're biasing so much, the current is still flowing, and then you're producing thermal energy rather than the RF, useful RF output energy. So in order to mitigate that, what people do is envelope tracking is you vary the power supply biasing in such a way that as the signal goes down, your current goes down, as the signal goes up, the current goes up. So that is what the variable supply is, the architecture of the envelope tracking, and that has been implemented and available for your consumption in this tool. So again, I'm not going to go through this, but one of the things that is very important that has been introduced is the ability to specify the complex impedance into the process, and you will be able to run the simulation. So here is, it's no brainer for anybody. Once you are in Linux or once you are in ADS, you really don't have to bother with where you are, whether you are in Windows or Linux. But this is showing that if you are in ADS, this is showing how you install the digital predistortion explorer into your Linux ADS. Same UI will come up, and then that's what it does. So just to conclude, there are some aspects that are improved into this waveform. So any one of you have made any measurements or simulated, let's say, the EVM of an amplifier. So with a very complex modulated, some kind of a 5G waveform, let us say. So you have to, and then measurement of EVM or CCDF is a statistical measurement, right? It's not, you just measure once and then it gives the final answer. You have to build that on a history of what is happening to the waveform. So all the peak, am I hitting all the peaks? Am I hitting all the valleys? And then before I conclude my measurement. So the measurement is made with a lot of, let me put this way, a lot of samples of the waveform goes through the amplifier. So this can take a long time to be able to measure that metric that you are looking at to improve. So how do we speed up that process? There is something called compact waveform. So you take a long waveform, typically if, let us say you need to put 100 frames, I'm just saying, of a signal which is maybe tens of milliseconds, it may take several hours for you to simulate through the very complex architecture of the power amplifier. But if you reduce the waveform at the input, but that has the same statistics as the 100 frames of the waveform, you're done. You know, what we are interested is statistically correct waveform and compact. So there is another feature in this product that is what we call compact waveform. If you hit that, you will be able to run this DPD process much quicker. Now again, why do you need to have the speed improvements, and then is it not like I push a button and then I get a linear amplifier? No. If you were to actually have gone through the DPD process, you have to do the DPD several times because there are a lot of tweaks you can make. You know, the algorithms are not like push button type. There are some knobs in your algorithms that you have to vary. For example, the nonlinear order, the memory order, and then the waveform itself, the compact waveform. And then so there are parameters that you have to keep on varying, optimizing them to get to your final answer. So you need to be able to run this process very quickly, like a design tool, push a button and then see the answer, and then whether it is satisfied or not. Or sometimes you can put it in a loop and then go away and come, but you don't want every single time it takes hours of simulations to produce the output. So a lot of speedups were done in this Explorer that is very conducive for very quick digital predistortion. All right, I think we are very close to the final. Yeah, the resource slides, and thank you. And those are the things that I have on the RF system design. And then, power amplifier linearization is a very important aspect. Even till today, still today, the power amplifier is like 30 to 40% of the system of the cost of the system, and either aerospace defense or commercial communications. So it's very important. So we put that as part of the RF system design here in this mix. Thank you very much.